Hello guys, welcome to another episode of Sound Talk Show. So we are going to do today Wolfram language coding, okay? So I'm just going to code Wolfram language graphics, and we are going to do this geometric inversion. Last time we did this, we did a video on geometric inversion. So it's a geometric process. Basically, you apply a function, so you can turn this grid into that, okay? So this is a geometric inversion, and this is a two-dimensional case. Very simple. You just map a function to another point. Given a point on the plane, you map it to another point by this function. This function is called geometric inversion. Okay, so this function is available in vector space of any dimension. So you can be 2D, or it can be, so all these are 2D case. You start with a different grid. This is 2D case, and here's another 2D case. You begin with a regular polygon instead of squares. Squares is a regular polygon of 4 sides. So you start with the regular polygon of 6 sides, then you get 6 or 7, then you get this, So that's all. These are two-dimensional case. Then you can augment the 2D case by adding a thickness. So you got this beautiful tile geometric inversion. So here is a code. For example, let's copy the code and let's just start to show it. What we are going to do today is to do a tube version. So starting Wolfram language, a new notebook, run it. Okay, hold on a second. So let me put this into the right place, my windows. So let's put here, and let's magnify. Let's say 150. 150 is good. So you can see here's a code, and this is a beginning configuration. So after transformation by the geometric inversion, you get these 2D case. Now you see it's still on the plane, it's two-dimensional. Then you just add more code to add a thickness to it, so you get this. So we did a video about a year ago. So if you go to YouTube, search for Xali, YouTube geometric inversion, you'll see the video we did. Actually, I have a link here somewhere. So anyway, so that's a 2D case. Okay, so we did the 2D case. Then you see the tiles, when they are near the center, they become infinitely small. So if you are going to plan to do this as a garden tile, then that wouldn't be good, because you cannot have infinitely small squares. So you want to modify the function such that when the points gets to the middle, they don't become infinitely small. Rather, you want constant shape. But however, you want to remain the kind of the style of these nesting circles, this pattern. So what you do is you change the function. So this involves mathematics. If you have studied calculus well, then you would know how to change the function. So we did that. So we changed the function, and we begin, rather you don't change the function, you change the beginning configuration. So if you begin with this configuration on the left, then you apply the geometric transformation, then you got this figure on the right side. Beautiful. Okay, to me, this is one of the work I'm very proud of. So you can still see the many circular patterns, nested circles. However, each of the tile is kind of the same size. Okay, so and here is so again we add a height to it, so we got this beautiful tile. So let's try it. So here is the code. The code is pretty short. Okay, so let's go back to Wolfram language. So you see this is previous, this is transformation of a bunch of squares on the plane, and now let's paste this code and run it. So this is, we begin with this figure, then we apply transformation, we get that, Then all we have to do is we want to add the code is not here, it's still 2D, so we want a 3D case. Yeah, so 3D case. Okay, so the code is here, so let's copy it, copy the code, go down here, paste it. Okay, the code is not about 50 lines. Now you can press Ctrl+Shift+N to turn them into a traditional formula. For example, let's do it. Okay, so let me make a copy so we can see the difference before and after. So select it, Ctrl+Shift+N. So you see, this is automatic typesetting in Wolfram language, and it's fantastic. And you can shrink if your window size is smaller or wider. The formatting changes accordingly, even with complicated fractions and nested fractions and radicals. You see there's a radical there. So this is the Wolfram language, fantastic. Okay, and you can download it free. If you watch my video, I talked about it many times. So here's today's talk show. I'm gonna keep notes here, so later on you can click on the YouTube description and go to this page, and you can see all the code. So here's a link to the geometric inversion, which we were talking about, and click on this to go to XR Wolfram language tutorial. You can search it and you'll find it. So here's a download for free, so you can download and you can have this free. Okay, so now let's actually run the code. Okay, so put a cursor here, Shift Enter to run it. Okay, Shift Enter. So you see, let's magnify. Okay, actually, so you see we got that. We begin with this figure, then apply the geometric transformation. We got this figure, beautiful. Then we extend it. We add a Z coordinate to it. So we got a 3D configuration of that planar figure. Okay, now all we have to do is we add thickness to it. So all this is graphical graphical programming, very interesting and very different in nature from what typical industrial programmer are excited about, which is game programming, OpenGL, WebGL. Those are very different nature, and those are very cumbersome. So if you want to do this, so we created this thing. Let's see if we can, let's magnify. Okay, so we created this thing. How many lines of code? About 50. Okay, about 50 lines of code. If you want to do this in OpenGL or something, that's gonna be 1,000 lines of code. So that is the advantage of Wolfram language. It allows you to quickly see, visualization or concept very fast. Okay, and the language is fairly easy to learn. It's very different from C or Java or Python if you came from those. But if you don't have those, experience, Wolfram language is actually rather very easy. You may find it hard to learn because it's very different from Java, C, C++, Python, Golang. Very different from those. So here's how you download Wolfram language, and you go back and you can see I did many videos, over 20. So you go to this page. These are some of the best videos. So if you are learning Wolfram language, watch them. Okay. Comments and questions, relevant questions about Wolfram language, post it there. Okay, and I'm gonna answer later. So watch this video. Okay. So now today, let's go back. Let's go back. So we talked about geometric inversion, which is a function applied to a two-dimensional grid, two-dimensional version. Okay, then all these are two-dimensional. although this looks like 3D, but it actually is just a height. The function is still two-dimensional. Then the geometric function is also a three-dimensional function. In fact, geometric inversion works in any vector space of any dimension. So here we have a three-dimensional example, very beautiful. Okay, so and here's a code. The code is even shorter. So let me explain what this is. So before we begin with a two-dimensional grid, if you scroll up, we start with a bunch of squares, right? Now in a 3D case, we begin with a bunch of cubes, okay? Then we do the geometric transformation. Then you got this figure, okay? So let's run the code and let's run the code, okay? So you can see, fantastic. Let's magnify and let's see the full glory of it. Okay, so you got this beast. You can see, the nested circle structure. Beautiful. As they get closer to the center, each of the cube becomes smaller, infinitely small when they reach the center. So, but anyway, you can see it. So this is a three-dimensional case of geometric inversion. Now, if you are studying math, geometric inversion is related, for example, in complex analysis. If you study complex numbers, then 1 over x where, 1 over x where x is a complex number, that is a geometric inversion. Okay, that's exactly the same thing. Well, except that it flips the plane. Okay, anyway, it's basically the same thing. 1 over x where x is a complex number. Okay, so that's a geometric inversion. Actually, we did the video, so you can find the video. And what we're gonna do today is to apply geometric inversions, similar idea, but a variation, computer graphics, graphics programming. So you can see what we want to do today is that you can see, before we begin with a grid, then each line becomes kind of a circle, it becomes, it transforms each point on the grid, right? Now, instead of the, line, we are going to use a tube. So we got a bunch of tubes. So this is kind of like a 3D case, but still 2D. But, so we got a grid of tubes. Then we do the geometric inversion. Then it becomes, it should be tubes. So we can rotate it and see. So let's see how it looks. I'm hoping it's going to be beautiful, just like this case. That's what we are going to do. So I already spent 10 minutes to talk about all these prelude. So I hope we can, it'll take a while. I would say another 40 minutes, okay, at least 50 minutes even. So I'm going to try to do as fast as we can. So first of all, start the Wolfram language. Now I'm coding Wolfram language in for example, let's say range, let's say 10. Run it. Okay, actually run it. You can see the answer is 1, 2, 3, 4, 5. We generate a list of numbers. So I'm running Wolfram language in Emacs because in Emacs, I have my system. It allows me to edit, modify, work with the code much faster. So I'm using Wolfram language, XR Wolfram language mod. So it's free, it's on GitHub, it's open source, and it's sponsored by Wolfram language, Wolfram Research, the company. So let me show you the code. Okay, so you just describe function, XR Wolfram mod, then you can jump to the source code. So here's the source code. The whole thing is about 2,600 lines of code. And if you go to the beginning, then here's the URL, go to it, open it, show in browser. You can search for it, XR Wolfram mod, and you can get it for free. So you can download it's on GitHub. Yeah, so here is a video where last time we were coding this geometric inversion. So you can download it on GitHub. Okay, so it's a GitHub, it's there. So download Wolfram engine, it's free, and download this. And if you are using Emacs, you are good to go. So question, Rene Poe. How much math background do you recommend before learning Wolfram language, or can it be used as a math learning tool? Okay, so yes, you don't need any background. Let me explain. Let me spend 2 minutes to answer that question. Wolfram language is a programming language that originated from doing computer algebra. It's called computer algebra system. Okay, so originally about 35 or about 40, Wolfram language began in 1986, I think. So about 35 years ago. 35 years ago, Wolfram language began as a tool for mathematicians and physicists to do mathematics. Okay, so physicists, mathematicians, and engineers, you need to do a lot mathematics. For example, SpaceX, NASA, if you are designing a jet, a rocket, going to space, you need to huge amount of calculus and engineering. So you need to solve a lot of equations, integrals. So in the beginning, Wolfram language was created. The product is called Mathematica. Okay, like math, Mathematica, because it's a tool to help you do mathematics, solve all the equations, or theoretical physics, black hole, how far, things like that. So the product is called Mathematica, and it's a tool, okay, to do mathematics. However, what does the tool looks like? The tool is actually just a programming language, So if you have seen the code here, just like let's say Python, JavaScript, you type some code, each code has specific, arguments, then it'll output. As you have seen, I can also run it in here. So, just like Python, let's close this. For example, I run this. You can see the answer at the bottom. I can actually make it more complicated. Let's say table x squared. Okay, so x from 1 to, let's say, 5. Run it. So you got the answer at the bottom, so you can see it's there. So Mathematica is a product 35 years ago. It was intended to do mathematics. And how do you use it? It's a programming language, basically. It's a very full-featured, highly advanced beyond all others, because you can see here, you have graphics there. Most computer language, you cannot. Java, C, C++, C#, Python, JavaScript. There's no graphics. You can't talk about graphics. Yeah, if you want graphics, you need to have external package that generate graphic, very complex, okay? So Wolfram language is a programming language that has all these features, and also, symbolic, typesetting, symbolic computation, okay? So originally it's designed to do math, but it's not just math, it's just any kind of programming, okay, except low level. You don't really, for example, you don't use Wolfram language to write a operating system kernel like Linux. That is not you cannot, because it would be too slow. It doesn't fit there. Okay, so if you want to do embedded systems, drivers, like programming microchips on your microwave oven or on your watch, that's not Wolfram language. Okay, if you want to do high-level mathematics, solve physics, advanced protocol, design a keyboard, designing a car, engineering, or audio systems, synthesizers, you can do that with Wolfram language. Actually, I talked too much about this. Watch my previous video, Introduction to Wolfram language, okay? So anyway, to answer your question, so Wolfram language is a programming language and it also do math. So do you need to know math? No. Just like Python, JavaScript. Do you need to know math to do them? Not really. You can code, you can manipulate strings, you can generate lists, tuples, vectors, hash table, programming. So you don't need any mathematics at all. On the other hand, if you are already a mathematician, fantastic, okay, fantastic tool. Or if you are a student, you are interested in mathematics, but you don't know much mathematics yet. Wolfram language helps you. For example, you want to do calculus, let's say limit, okay, so limit, let's say 1 over x, then x goes to let's say x let's go to x goes to infinity, okay, so let's see what is the limit. So that limit is 0. So that's calculus, and derivatives, differential equations, linear algebra, integrals and all that. So you don't need to know any math to use it because it's a programming language. If you are a mathematician, you can use it. It'll help you a lot, or physicist or engineer. And if you are a math student, it will help you significantly learn mathematics because you can, just, for example, if you want to expand, let me show you just another example. And we start to code, okay? So let's say x plus y, let's say 40th power, okay? Let's say, we can make it more complex, minus 2, okay? So this, this you cannot do in Python, although it's pretty simple. You want to multiply this by itself 40 times, you cannot do it in Python. But in Wolfram language, that helps you learn math a lot. And you can simplify, given this huge output, you can say, like you have no idea what those are. So you can say simplify, and the ampersand stand for previous expression, or you can press Control L, So actually, let's do Control Shift L so we get the whole thing. So you see, so suppose you are a physicist or mathematician, you got this expression, you have no idea what it is, So all you have to do is you just say simplify, okay? So let's run it. Okay, here's the output, It factors a polynomial. That's what's happening. Okay. Thank you guys for watching. So now let's start to code this thing, the thing we wanted to code. Okay, so let's start to code. So we talked about we actually gave us a small intro to Wolfram language, and now that's the Wolfram. Let's start to code. There's a lot to code. It's gonna be 40 minutes. Okay, close. Let's begin to do it. Okay, let's code. So what we want to do? Okay, so actually copy this. Go back here. Let's paste this link here. So we have a record of what we talked about. Okay, close. So we're gonna code this now. We haven't even I haven't explained what's a geometric inversion. I mean, what does the function actually do? But this is a function, okay? So you probably don't understand what that is, but okay, I would say just watch my previous video. Okay, you watch, I showed it before. Watch my previous video. I explained, for 20 minutes on what is a geometric inversion. So basically, so we defined it. You see, we defined it here, and the base. But let me just show you how it runs. So you given a point, let's say 3, 4. That's x equals to 3, y equals to 4. So you run it, that's the result. So it takes a point, returns another point. Okay, that's basically that's what it is. That's all. Okay, so I'm now going to explain exactly what it does. Actually, that is very extremely interesting. Okay, so for example, all these are geometric. Let me just briefly go to it. So all these are geometric inversion, and if you want to understand it, and it's also there is a Wikipedia article on it. Of course, just search for geometric inversion. Okay, so where is the okay, so you can see it here. Geometric inversion. Oh yeah, this page. Okay, so it explains here. Okay, yeah, watch my previous video. We explained that before. All you have to know now is that it takes a point and returns another point. Okay, just the function. So now we want to begin to do tubes. Okay. Okay, where are we? We want to, remember. Let's delete this output, this huge output. Delete. Okay. Now remember, we begin with a grid or squares. So now we want tubes. So first of all, how do you create a graphics of tubes? Okay, let's see. I don't remember. Now Wolfram language has 7,000 functions built in by default. Okay, so here is how you represent a tube. Okay, so let's go to let's copy that. Okay, so let's start to code here. Tube. Okay, so let's press Control H. No, press Tab H to look up the tube's documentation. So here's the Wolfram language website documentation on tube. Okay, so here is how do you represent the tube. So it's just that. Actually, not that. Because it generates this. Yeah, this is annoying. So actually, you just copy it. Tube. Okay, given a three-dimensional point. Oh, it requires three-dimensional point. A bunch of represent a 3D tube around the line joining a sequence of points. Okay, so the arguments is a list, and each component of list is a point in 3D space. Three numbers, list of three numbers. So you have a bunch of points in space. Then it generates a tube connecting around those points. Okay, that's how you represent the tube. Okay, and then you can give a second argument, that's the radius. Okay, so first thing we want to do is, let's say, so each one of the element is a three-dimensional thing. Okay, let's generate a tube. Let's generate a circle. Okay, so circle is sine cosine. Okay, cosine sine. Okay, cosine sine, let's say x, and the third component 0. 0 is a z. We don't want it to move, so 0. So cosine sine. So let me do this table. Okay, table takes two arguments, cosine sine and 0. Then x goes from 0 to 6, let's say, in steps of 6 divided by 20. Okay, so that will return, that will return this thing. Okay, so you'll return a list. Each element is a list again, and in that list is three numbers. Basically, the whole thing is a list of points in 3D. Okay, So that is the okay, that is a bunch of points. Now we just say tube, okay, then gives that, okay. So copy that back to Wolfram language, paste it, run it. Okay, wait, shift return. Okay, so we got this. Okay, now we just say graphics. We want to put graphics 3D in front of it. Okay, it's 3D. Okay, then the last expression. Okay, run it. Fantastic, we got a tube, a circle represented by a tube, not just, you know, line. Okay, so that's basically how you get a tube. Okay, and now what we want is we want this you know, here's a bunch of squares, but we actually what we want is a grid represented by a tube. Okay, okay, let's do this quickly. Oh god, it's gonna be 30 minutes more. So we want a tube. Now remember the syntax for a tube. So we got, first of all, we generate a bunch of points of the grid, you know, point, okay. Then between each point we use a tube to connect them to represent the tube. So there's a tube, okay, tube, and also vertically too. Okay, so we got, you know, each between points is a segment of a tube. Okay, then we apply the transformation, the geometric transformation. Okay, that changes all the endpoints or the vertices. Then the tube will accordingly change, you know. So that's what we want to do. So far so good. Am I doing good? So okay, I thought you're gonna use Glove 80. Not yet. You know, I have to set it up. So you know, I was thinking of using it, but then, you know, sometimes I don't know the key. I have to, you know, I want to focus. So let's stay focused on, you know, this video is just Wolfram language. We have a lot to do. So so let's start to generate. So this one is example of a tube of circle. Okay, so let's put it back to okay, that's and we're missing graphics. Okay, okay, so get that there. Okay, so that is the, you know, you can open it, you know, see. Oh, we spelled it wrong. It's not graph, it's graphics 3D. Okay, so that okay, copy, magnify this, paste it there, run it, you know. Okay, so this is the example of tube of circle. Okay, so put it back here. Now let's start a new one. A new one is what we're gonna do. Okay, so now we know how to do a tube. Now now the first thing we're gonna do now is generate a bunch of grid points. Okay, so that is going to be table. Table. Okay, this table is going to be X and Y and Z. So you need 3 points. Okay, Z is 0 always. Okay, then the second element for the second argument for the table is going to be X going from negative, let's say 5 to 5 instead of 1. Okay, then Y goes from same thing, negative 5 to 5 instead of 1. This will create a list of numbers. Okay, let me show you. Okay, list of three-dimensional nested list of numbers. So that is essentially the grid points. Okay. Yeah, you can see it's 0, 5, 0, negative 5, negative 5, negative 5, negative 4, negative 5, negative 3, you know. Okay, so we got list of points. Now we need to, for each, between every 2 points, we need to put a tube. So between every 2 points, it needs to be tube and those two arguments. Okay. Okay, so God. Okay, why don't we do this? Okay, so instead of that, okay, so let's just say tube here. Okay, no, not stub tube, and not stub tube there. Okay, so tube takes a list, okay, 1 point and 2 points, and the second point will be, you know, from 1 point to the next point. So the second point will be, let's say, x plus 1. Okay, so that's one tube. Okay, so actually we're gonna generate a list. Okay, so the list will contain 2 tubes. Okay, like that. So the second tube will be x then 2y plus 1. Okay, I think that's it. This will give us a bunch of tubes. Let's just try it. Okay, does that make sense to you guys? Control Shift N. Let's make it. Okay, it doesn't do anything. Let's run it. Okay, so you can see tube. So that's one tube. You know, that goes like that. And the second tube is going vertical. Okay, let's double check. 0, 5, x, negative 5, then to negative 4. That's correct. The y and z are the same. Okay, now the second tube, negative 5, negative 5. That's 1 point. Negative 5, negative 4. Y is 1 less. You know, 1 more. So we got kind of tube like that. Okay. Then the next part is just the next one. So we got a bunch of that's what we want. Fantastic. We got, you know, this is not efficient code because you can see the arithmetics, they kind of repeat it, but let's just push on. You know, the thing about Wolfram language is that you get, you know, you do things that you spend the minimal amount of time to have a product, a protocol, you know, to create something. Then you worry about computing speed later. Okay, that's the most proper taking advantage of the Wolfram language. You worry about optimization later. So you got that. So actually we can show the tube. So let's say tube segments. Okay. Let's say lots tubes. You know, let's just be brainless. Let's just say lots of tubes. Okay, so we define that. Then we say, okay, then we don't need this whole thing anymore. Then we just say graphics, okay, and lots of tubes. Okay, I think that will work. Okay, let's remove that. Copy the whole thing back to Wolfram language. Okay, got this. Okay, select all, paste, Shift Enter, run it. Please show me the beautiful graphics. Ha! Success. Successful, beautiful. Is that beautiful? How many lines? How many lines of code? Oh, 2. Fantastic. and you can rotate it in real time. Try to do that in Python or Scheme Lisp. Okay. Okay, fantastic. Now we are going to now we have this. It's extremely easy. All we have to do is apply our geometric transformation function, which is just this line, to all the points. So easy, so easy. I thought I'm going to, oh my god, 30 minutes or something, but now. Okay, now let's do, this is a function, we define it, okay, geometric inversion. Then, okay, this function, yeah, this is good. So this function, we need to apply that function to all these points, okay? Now, it's very easy to do. So here is a structure, okay, so all you have to, so we are going to use pattern matching. So here's what we are going to do. Now imagine doing that in C++. You said it first. True. C++, the worst damage to computing industry. You know, starting with C and Unix. You know, they begin, then they spread the virus, then it rots every programmer's brain. Because when you show these to the programmers in the industry, they don't understand. They'll say, oh, that's nice. But tomorrow, they forgot all about it. They are back to memory, Rust, you know, or memory, malloc, you know, memory. that's what the C references, you know, pointers. Oh, they're gonna do that. You know, that's what the most industrial programmers are like. You know, because they are accustomed, their brain, for the past 40 years, their brain is kind of like being trained into that way of looking at things. You know, when they see these, they say, oh, that's nice. But after 5 minutes, they forgot. They forgot all about it. And yeah, most programmers, they are not interested in math neither. So anyway, so let's go back. So let me show you what we are going to do. Very easy, okay? Just one line. One line, we'll have it. We'll have this geometric, you know, we'll have this geometric inversion of bunch of tubes, okay? How are we gonna do? So so right now our the task is that you have this data structure. You want to apply a function to each of these points, okay? Each of these points, you want to apply this geometric inversion function. How do you do? Very many ways, okay? But we are going to use a pattern matching. So this is unusual. This you will not see in this Python C, you know, you will not see anywhere. You know, you will see it a little bit in Haskell. In Julia programming language, okay, you'll see OCaml, for example, a little bit, but nothing like Wolfram language, okay? I'm going to show you. So that's what we are going to do. Apply this function to each of these points, okay? Then you'll be done, okay? So we are going to use pattern matching. So what we do is that we suppose tube graphics. Okay, we define, you know, first of all, we define lots of tubes. Okay, then we define tube graphics, you know. Then we define this function we need to apply to those points. Then we just say tube graphics replace, this means replace, okay? Let me use the easy to understand way. Okay, so let's say replace all. Okay, that's more. I'm going to use, you know, this is a shortcut notation, but let's not do that. Normally, if you are programming Wolfram language, that's what you usually type. But let's use the easy to understand syntax. So what you say is you call the replace all function. It takes two arguments. The first argument is whatever expression you want to do the replace. Then the second argument is a rule, basically the find, what kind of pattern you want to find and what to replace it with. Okay, so you can say find replace. Okay, that's a syntax for the replace all. So okay, so find. So what do you want to find? I want to find a list of 3 things. Okay, and each one of them is actually I want to find a tube. So let's put it here. So I want to find these things. So let's okay. So I want to find a pattern where here is 3D points. Okay, P1. Let's just say P1. Anything P1. Okay, anything we give it a name P1. And here similar P2. So 2 points. Okay. Now what you want to replace? Actually, let's change this arrow to colon arrow. That way it's delayed. Anyway, that means we, that means don't evaluate the right hand side right away. Only evaluate it only when you find the pattern. Why? Because the right hand side we need to apply this function. Because otherwise, if you evaluate right away when the function don't have any arguments yet, it doesn't work. You need to replace this data by this pattern tube something, and by, so what's the result you want? So let me show you. So what you want is you want this. Okay, geometric inversion applied to P1. Okay, and same thing here. Okay, that should be it. That should be it. So actually we just copy all, new notebook. Okay, let's magnify 150. That's it. Run it. Okay, please show me. Okay, didn't work. So, I know why. Because our function, wait, I don't know. Let's try. So if we call our function with, let's see, tube takes at least, let's see what happens if we call our function like that. Okay, that returns that. Now what if that's a function, that's a geometric inversion? Okay, yeah, that's correct. So it works in any dimension, so wait, do you actually need a bracket or not? Yes, you do, I think. What? Yeah, you do need a bracket. So why is it not working? Let's try 1, 2, 3. Okay, so you actually do need the braces. 1, 2. Yeah, so that's a number 1, 2, 5. That's a number. You do need the curly brackets. Okay, so why is it this pattern transformation didn't work? So Oh, I got the syntax wrong. Instead of underscore P1, it should be P1 underscore what? Yeah, P1 underscore, okay? I got the syntax wrong. It should be like that, okay? Copy all, select all, paste, run it. Yeah, error. Oh, we got pi, wait, type error. So we wrote pi instead of P1. So let's try it again. Copy all, select all. Paste it, run it. Go down, go down, go down, go down. Fantastic! Fantastic. So I think I'm glad. Okay, so we did it just 1 hour, 50 minutes. We did this fantastic, and that's it for today. Yeah, I don't want that, let's keep it short, let's not prolong. So this is what the final result. Okay, the final result, that's what we want. That's successful. Okay, you can see the image is not too symmetric. Why? Well, the reason is that because you see, remember the way we generated the grid, we have these things poking out. That can be easily fixed. You can fix it in several ways. So, okay, let's do 5 more minutes to make it nicer. Okay. Yeah, but this is the result. Actually, I'm happy. So one way to, yeah, we can fix it. You just add, more segments at the end. But that would be, yeah, you can do that. There are many ways, but this is one of those cases where you have off by one case. When you have nested list, you have the special issue, special case of the endpoint. So, you can manually fix it by adding, or you can do more elegant way. It's a bit, it's a kind of tedious thing. Another way, alternatively, to fix this is that instead of line segment, we can just make them each a square. That way you don't have the poking out thing. But it wouldn't be exactly the same as that. We can do the square. Let's try. Okay. So this is done. This code, just actually 4 lines of code. 3 lines. It's done. Okay. So let's pop it back, copy it, paste it again. Now this time we're gonna do the enclosed. We start with squares instead of the grid. Okay. So to have a square, we just do 4 cubes. Okay, 1, 2, 3, 4, 4 cubes. Yeah, actually we don't need. Actually, we can just have one single tube. Okay, one single tube. It will go around like that. So you need 1, 2, 3, 4 points. This cube, this tube, one single tube, will represent a square. Okay? So tube takes one argument, and in this argument, it'll be, it's a list, and it's going to be, this list will have 4 components. Okay? 1, 2, 3, 4. So the first point is 0, 0, x, y, 0. Okay? Now, x plus 1, y 0, then x plus 1, y plus 1, 0, then x and y plus 1, 0. So okay, so you got going around forming a square. Okay, and that's it. Let's try it. Is that it? I think so. Let's try it. We got null. What's the null? Okay, so tube. Okay, so I know what's going on. So there is a tube. Okay, so there is a tube. Now you got this null. It won't be correct. The reason is because your data structure changed. Remember before it's a tube of 2 points. Now you got tube of 4 points. So what you have to do is easy. Okay, change the pattern here. So now the pattern is, we can actually just do this P3, P4. This is kind of manual. You can alternatively you can do it in one shot. Doesn't matter how many points. But let's just do it manual because for simplicity, So P3, P4. This is not efficient code, but anyway, that's allows you to do things very fast. Okay, let's paste it. I think that's it. Run it. No. Okay. P1, P2, so non-least iterator null. Okay, why am I getting a null? Okay, so it's P1, P2, P3, P4. What? P1, P2, P3, P4. What? So we got the tube. We got tube, right? We got let's double check our code. We got a null somewhere. We got, you see, the problem is we got extra comma, repeated comma. Wolfram language doesn't like that. You see, 1 comma here, 1 comma here, repeated comma. Okay, Wolfram language doesn't like that. So that, copy it, select all, paste it, run it. Fantastic. Scroll down. Fantastic. Okay, that's it for today. Thank you guys for watching. Now, yeah, it's still not perfectly fixed. You can see, the reason it's not. Wait, we're missing. Oh, 1, 2, 3, 4. You need to connect it back. Okay, so what? Yeah, okay, so let's just repeat that. Okay. Yeah, okay, this is not efficient code, but let's just do it. Copy it. Okay, oh wait, 5. Copy it, select all, paste, run. Fantastic, beautiful. That's it. That's it for today. Wait, this is still wrong because because the whole thing is now not centered. Okay, so we can fix that by starting at 5.5, 5.5 to instead of 1. Okay, so 5.5 instead of 1. Okay, select all, paste, run it. Okay, let's suppress the output by putting a semicolon. Okay, select all, paste, run it. Fantastic. Now, is that right? Yes, that is correct. Okay, that's it for today. Is this correct? Yes, this is beautiful. Thank you guys for watching. Bye. Wolfram language, okay? Please make a video on G502. It's a macro, and it's macro you use for efficiency. Well, G502, you are talking about this mouse, right? You're talking about this mouse. There's not much to it, There's tons of other people doing that. So Okay, that's it for today. I'm shutting down. I'm shutting down now. And if you like my video, go to my website, donate to me. Okay, so you can see, you can Patreon me or Amazon gift card me $5 a month, support me, or $20 one shot. Thank you. Bye.